All right, so let me share my
Oh
pad,
yeah,
try to
applicants.
explain
Oh wow.
each like the concept. So this is really like the rough introduction
Uh,
to differential geometry.
oh, wait, I'm not sure.
Mhm.
Uh-huh.
So I
Okay.
also you can see my screen.
Yes.
So the the like the
Okay.
logical flow
Mm-hmm. Mm-hmm.
for step by step is that so there is a so step one, so there's a given a surface, and you can just assume in the problem set it should be either the two-dimensional sphere or torus, as you already saw. So given a surface, let me make it as just the box so that you can see the dependency. So you can choose either the sphere or the torus, but you can also change it. But our purpose later on, we will just actually look at the sphere. So,
Yeah.
and then we assign so-called the concept of the first fundamental form. And I assume I need to explain this a lot
Here.
today.
Please feel free.
So this gives you this one. So we start from the surface, and then that will determines the concept of the first fundamental form, whatever that is. And then that would determine so-called the crystal symbol that will determine the crystal symbol. And after our discussion, I will share this note to two of you. So if you have any
Oh, okay.
questions,
Okay.
just know. Yep. So and then that will determine so-called the Riemann curvature tensor. So you guys also want to get familiar with the notations so that let me also put the notations here as well. So for the first one, the form, we prefer to denote this I as a E so let me just write as just a the same expression from the note that I share. So it looks something very messy. So like the E du square plus 2F du df du dv plus G dv squared looks very messy. But anyhow, this is the first fundamental form. And this CRISPR symbol looks like gamma ijk, and it looks quite ugly for the expression. We need to figure it out. And that will give us Riemann curvature tensor. Let me make this box. And it's written as R stands for Riemann, IJKL, something like that is quite kind of crazy, like the notation. And then we will determine, so let me just look at the terminology. Depending on the context, we actually use the different lecture terminologies. But let me say the curvature. So we have the concept of so-called the Gaussian curvature. I'm not sure I use this term here. Let me just search curvature. Yeah, I use the term of the Gaussian curvature, right? Gaussian curvature. And from here, later on, we will split into two experiments for the project based on the value of the Gaussian curvature. Experiment A and experiment B for Angela and Jesse. And those experiments are done by like the Python and those like the quantum simulator tools, but those are based on the computations of the Gaussian curvature. So So please do not like get overwhelmed in a sense that I don't expect you to understand all this like the concept very deeply by end of this summer, and that's definitely okay. So I just want you to get gain one experience of computing the Gaussian curvature by just following the recipe. That's it. And I think this knowledge can be very, very useful for your future study, not only this direction, but your like the future study in general direction as well. So, all right. So that's what we'd like to discuss step by step. So let's just put the numbers here. So say number one, say number two, say number three, say number four, and say number five. And we will talk about those two experiments after problem set three. Still, there is a necessary concept that you still need to know in order to explain what exactly we can do in the context of the quantum computing. Is that okay with you? So let's just focus on this recipe to get the concept of the Gaussian curvature for a moment. Is that okay with you? And
Okay.
actually,
Yes. Wait,
we
so
will. Yeah, go ahead.
so with experiment A and B, is it Angela and I, like Angela does A, for instance, and I do B, or is it Angela and I both do A and then the other group like they do B
Those
instead?
are you two can discuss together, but there is a very like the specific like the experiments I have in my mind, and they are extremely overlap. However,
Okay.
those are all commonly based on the computation of the value of the Gaussian curvature. So, for example, you two can split each experiment into just two pieces. You can do individually proceed, but either cases, at least I need to look at all those progresses by myself. But you two can look at same like the project together. And let me just say this. So, for the purpose of the presentation of this like the summer like the mentorship program, you don't really need to complete the all experiments by the end of the July. I don't think that's really necessary. Once you just understand like this like the recipe, that's very sufficient to do the very excellent presentation by end of the July, in my opinion. And once you get the big picture, I mean the idea, then I kind of assume so you too want to proceed in around the one semester because I'd like to submit your work to the some like the decent like a genre so that you can use your later like the portfolio purpose. But it might take time. But you don't need to like to rush everything. So let's just focus on the presentation side. You know what I mean? And then so once you get the motivation, then you can just proceed. Of course, under my supervision for sure. So please do not worry. But yeah, that's your question, right?
Yeah. Mhm.
Okay, so let's just today just clarify each like the numbers today, including the computational recipe. So let's just look at each steps. So step one. So it's about the surface. So for surface, so for our like the project, we will only actually look at just a two-dimensional sphere, truth be told. But if you guys have any questions, let me know. But you just assume for our like the concrete like the project, we will only look at just a two-dimensional sphere and the torus. So it looks very like the clear in a way. The sphere indeed look like something like this on R3, and the torus also look like something like this. And the point is, so you have a very specific parameterization of each of the surfaces. So for example, if you look at the page two of the example of the unit sphere, so that's called the so-called the spherical parameterization. You might saw this before, so that we are able to describe the sphere in a very concrete way on R3. Is that okay with you? And
Yes.
for the torus, so the torus, like the parameterization is also given in the end of the page three. So what I just want to put emphasis here is that we have the concrete description of each surfaces that we can proceed the computations. Is that okay with you? So I don't think I need to explain anything further, but the behind like the story is very, very deep. So what are the general like the surfaces we can look at and what are the geometry structures? But let's just forget. Let's just look at these two like the surfaces. I think that's very sufficient. And again, our like the like the experiment would be done on the just a two-dimensional sphere. Just that's it.
Okay.
And even
Okay.
for that, you can actually do the something new. Do you have questions?
No.
All right, then step one is already clarified. Let's now move on. Next one. So step two looks a little bit weird. Step two. So first fundamental form, what is it? So this is a little bit messy. And as name pointed out, so probably this is actually most important object in a way that this actually governs everything. So that's why we call it by the first fundamental form. So let's just look at the expression. So according to that, it says something very abstract. So it says E du square plus 2F du dv plus G dv squared. What the heck was going on here? And it just says, so equivalent to speaking, this G is same as capital I. This is a notation coming from Gauss. Gauss was the advisor of the Riemann. So it is named by Gauss here. So that's we call it by G. But you can also read this G as a first fundamental form, and we time to time call it by so-called the Riemannian metric. They are the same. So two different like the terms, but it exactly mean the same thing. Either we can call it by the first fundamental form or the Riemannian metric. They are just the same. Mathematical definitions are the same. So that we can just denote this guy as a 2 by 2 matrix. And for our like the project, this is very sufficient. I assume you know the metrics like the algebra based on the first like the problem set so that you already know how to handle in some way. So we need to really understand what was going on here. So the expression looks the following. So EFG. So it says, so let me use more familiar notation for two of you. So you might saw the notation of a dot product before from the high school, or maybe not, doesn't matter, but at least you saw it from the first like the problem set. So this of u dot this of u, this of u dot this of v. Make sure to understand my notation. I use u without the curly like the notation, and v I use this one. So that this is my v, and please distinguish my writing. Is that okay with you? R sub
Yeah.
v dot R sub v, and G is defined as R sub v dot R sub v. So we are asking, so what is this? So in order to understand it, so I first just assume that if you just have the R3, so R3 just means the collection of XYZ. Each XYZ are, let me just use fancy notation of the real system, set of the real numbers. Is that okay with you? This is R3. And if you have x1, comma y1, comma z1, and x2, comma y2, comma z2, if you take the dot product, what do you get? Did you see this?
Multiply the
X1,
components.
X2 plus Y1, Y2 plus Z1,
Plus
Z2.
Z2.
Yeah.
Perfect. Yeah. So this looks like the elementary. Elementary does not mean trivial. So from here, so I wanted to get the like the perspective that so we call each of the element of in R3 as also called a vector. Okay, this is called by the vector, and we take the dot product between two vectors to get some value. Is that okay with you up to here? All right. So then what's the point of introducing the dot product? So that, for example, you saw this in notation also before. So if we want to look at the magnitude of the vector, what is the definition? We take the dot product, xyz, dot product with xyz, and take the square root. This is a definition of the magnitude. The magnitude of a vector consists of x, y, z for each component. Is that okay with you? This is the concept of the magnitude, the importance of this definition. So you can just now appreciate this concept. The concept of the magnitude depends on the dot product. So if you have the arrow, say x comma y comma z, so if we want to measure the magnitude, in order to measure this quantity, then you should equip with the dot product. Otherwise, we cannot talk about the magnitude. Is that okay with you? And then also what you know is, so if you have a x1, comma y1, comma z1, even I already wrote it, but let me just rewrite again so that you can also appreciate. So of course, you know this is defined by this expression for sure for the quantity, but this is also the same. This is also the same as the following. So magnitude of x1, comma y1, comma z1 times magnitude of x2, comma y2, comma z2 times cosine theta, where this theta is the angle between two vectors. between these two vectors. We usually just assume for the convention between negative pi to pi. It's just a convention. Like this. Is it okay with you? So this is another description of dot product. So what? So why we all of a sudden consider this like a concept? So I want you to get the geometric intuition that if you have one vector x1, y1, z1 like this, if you have another vector x2, y2, z2, then there's just an angle between these two. Is it okay with you? Then you have the magnitude x1, y1, z1, this guy, and you also have the magnitude of x2, y2, z2. So what you can do is you can take the orthogonal projection here. So please tell me, what is this guy? What is this quantity? I assume you know the definition of the sine and
Sine of
cosine.
cosine of theta.
Cosine of the theta. So that, as you said, this quantity equal to this one times cosine of the theta. Can you see that? So that you start from the length of the hypotenuse here. This length correspond to the magnitude of this guy. And then this, like the length of the base, correspond to the length of the hypotenuse times the cosine of the theta, by definition of the cosine of the theta. Is that okay with you? Then with this perspective, just relook at this identity. What does this mean? So you should equip with this perspective, given two vectors. What is the meaning of taking the dot product? You just take the orthogonal projection and multiply those two quantities. That's the meaning of the dot product. So let me just repeat. This is most important computation eventually, that if you have two vectors, then equip with the dot product, what can you do? You can measure the magnitude of each vectors. Is it okay with you? You can measure the magnitude of each vectors by just looking at this definition for sure. And from this description of the orthogonal projection, we actually also know the angle between two vectors. So if I say precisely, this is very philosophical like a statement. The dot product determines geometry. So I don't know anything about the Chinese language, but as far as you know, for the term of the geometry, geometry represent just how much. So geometry in mathematics just refers to the any branch of mathematics that we'd like to deal with based on the certain quantities that we'd like to consider. So for example, like the angle, magnitude, area, volume, arc length, as long as, and we'd like to know the price of something, we'd like to know some of the quantities that we'd like to care, or those are just some branches of the geometry, because geometry is the mathematics that we like to care about the quantity. And here, what you can see is that the product actually governs the magnitude, and also it governs the angle. So that product determines the all necessary quantities that we'd like to care. And that's the concept of the first fundamental form. From now on, I'd like to explain. So in order to explain the,
Sorry, I have a quick question.
Sure.
Is the dot product the same thing as like the inner product
That's a
or
good
taking an
question.
inner product?
So the mathematical like the answer is no, it's not true. So that product is one of the special kind of the inner product. And in general, inner product does not need to be precisely that product, but in this context of the first fundamental form, it is actually yes. So now let's try to see why they are in this case actually the same. So I want you to now imagine with like the situation that, so I want you to just imagine very naively. So just say, now let's look at the step two again. Step two, go back to step two. So let me very naively draw a surface in R3. So in X, Y, Z. So suppose you have a very like the surface look like this. So for each like the point of x comma y comma 0, that will determine the height. So this is just a graph of some function. Is it okay with you? Like this. But you can also find the explicit form of this f for the sphere and the torus if you want, but I just want to draw the abstract picture. Is that okay with you? So
Yes.
what we do, so if you have any questions, let me know. So what you do is, now let me use the same notation. We introduce another R2. That's a UV plane, and let's just assume that is defined on this like the board, open board here. So if I use the same notation, so that we'd like to map each point, on this surface from this like the ball. So that each point we just map by using, now let me use the same notation of the parameterization R that takes U and V, so that you can just assume if you have the pair consists of U and V, that determines the point on the surface in R3. Is that okay with you? Up to here. This is abstract like the picture, but you can kind of get the sense of it. So why we can do this, because even though we have a surface, but it's kind of the two-dimensional object, whatever definition of the dimension is, right? So that we want to have the two independent parameters that we use u and v, that each u and v determines one point on the surface. That's the like the mathematical modeling we're not doing. It's kind of okay with it. Otherwise, also let me know. It's fine. This is abstract like a concept. Could be a little bit difficult to digest for the complete like the beginners, but it's very likely understandable. So then if you, for example, so now it's a little bit like the difficult. So this notation in page 2 represent the following. So if you look at this guy again, so it consists of, because everything is in R3, so that it consists of x component, y component, and z component. Of course, each component, each like the point sit on the surface, but it should consist of 3 components on R3. Is that okay with you? So each u comma v. So this parameterization determines each of the components for sure, so that you have the one point on a surface. Then the notation of r sub u and also the r sub v. Now let's try to figure it out. So this is the very fancy notation, just a precise notation of dr du. Have you saw this notation before? Partial derivative. So du dr dv. Yeah. Questions? So let's describe it. So what are them? What is the first one? This notation means so-called the partial derivatives, meaning that we just regard that variable as a variable and others are just constant. That's the meaning. So that first one is round the x, round the u, meaning that we just regard v as just constant and take the just a derivative with respect to u. That's the meaning. So if you are not familiar with it, I will just show the computation together. And du over dy over du and dz over du. That's the meaning of the r sub u. And r sub v means dx over dv, dy over dv, and dz over dv. That's the definition. Let's just look at just one concrete example for you to get the sense of it. So for example, if you get this to be u comma uv comma v squared, if the parameterization is like this, then if you take r sub u and r sub v, what are them? Let me show you the first answer for you, and please give me the answer back for the second case. So the first case, so
One.
yeah, one, yeah, very good, one, and then
V
V.
and
USB score.
v squared is just constant.
Zero.
Derivative constant is
Oh,
Zero.
0. Perfect. Please give me the answer for the second one.
Zero.
0. Very good.
U.
U,
2V.
2V.
2v. Yeah, that's the way to compute.
Okay.
And make sure that in the case of the sphere and the torus, you know the concrete expression of this parameterization R for each cases, so that you are able to compute these two. Is that okay with you? For each
Yes.
cases. Those can be computed explicit. So let's try to see what's the meaning of it. So if you look at this guy, this picture again, let me now just redraw this guy. So for example, if you look at this line on the board, then if you transfer by using this parameterization R, then it goes something like this, for example. Do you agree? So as this line on the board goes by, then if you use this map R, then it transfer to the curve on a surface. Is that okay with you? Then what is the meaning of this guy or this guy? That just means then we are looking at the infinitesimal direction, derivative, tangent vector. What's the meaning of the derivative? We are looking at the infinitesimal slope, but now we are just looking at that in the multivariable setting. You know what I mean? So if you look at, so this could be abstract concept. Yeah, so if you don't get it, let me know. So the concept of the derivative gives us the infinitesimal slope. So now we just extend the same concept to the multivariable setting. So as this curve goes by, then that will give you this like the curve on a surface. Then if you take the derivative with respect to u, that will give you the infinitesimal direction. So similarly, so if you take this curve, this guy, then from this parameterization, it also goes like this. Then if you take the derivative, what do you get? What do you expect to get? You will get r sub v. They are the meanings of the r sub u and r sub v intuitively speaking. So with this perspective, let's just relook at what's the meaning of the first fundamental forms. So according to the first fundamental form, now you know these are the definitions. These are definitions. What is this guy? According to the definition of the magnitude, you know it is the magnitude square of r sub u. You know this guy is the magnitude of r sub v square. You know the second one is magnitude of r sub u, magnitude of r sub v, times cosine theta because it's dot product. What does that mean? This is the magnitude of r sub u. This is the magnitude of r sub v. What's the like the intermediate step? This gives us the information of the angle between these two vectors, r sub u and r sub v. So what's the point of the first fundamental form then? So now at least I assume now you can see the like the mathematical like the interpretation of the each capital E, capital F, and capital G. Capital E and capital G represent the information of the magnitude. Capital F represent the angle between these two vectors. So these three functions represent the information of the dot product. So now if you just relook at this picture, what we are doing is the following. So first fundamental form determines geometry of a given surface. Why? Now you have an interpretation how to really think of. So let me now redraw the same picture. So in R3, you draw the surface. This surface can be the two-dimensional, the sphere or the torus or anything else, in fact. So now you have this like a drawing in the same way. And also redraw UV plane. And there's just a domain of this parameterization, and we move everything in terms of this parameterization that determines each point. Then what you can now see is that for each point, that will give you this point. This point will give you this, and so on, basically. Then what now you know is that if you just look at the curve, like, so let me just now use, so this curve and so on. And what you saw is that let me just draw, say r sub u and R sub V for each point. So here you also have R sub U and R sub V. And just repeat for each point on the disk. Is that okay with you, intuitively speaking? Then what is the role of the first point form? So each point, we just make the tangent space. On each point, we just create the tangent space. So this is a vector space. Look like it's just nothing but R2. Then what is the meaning of the first point form? We get the inner product. So EFG means the inner product on each tangent spaces. Then what can we do? So as long as you have a tangent spaces and the inner product, then you actually know the geometry of the tangent spaces that determines the geometry of the surface. So that's why we call it by the first fundamental. So this is very philosophical concept. This was first like invented from Gauss first, and then Riemann create like the investigate this very extensively. So nowadays this is called by the Riemannian geometry. This determines like the affects like the work of the Einstein, and nowadays it's very important in the statistics and also machine learning as well. But the idea of the first fundamental form is that we just want to look at each like the inner product of each like the tangent spaces that determines the global geometric structure of the surface. That's like the what this object really mean. So it implies as long as you know just these three functions, where was it? These three functions. So then you know inner product on each tangent spaces, then we actually know everything on the surface. This kind of the abstract explanation. So if you need more explanation but it might take time to really think about what this really meant, but yeah, let me know.
I think it makes sense. Wait, I'm wondering, is there like online like a visual of this whole thing, like tangent spaces and the geometric structure? I don't know. Like, is there like a YouTube visual maybe
I
that we could
think
like
there
search up?
will be a lot of such like the visualization. So I recommend you just search it. So I recommend you search.
Okay.
And also just use the ChatGPT to just try to visualize. And this is very, very, very well known. So you can find bunch of the visualization. So how to really describe the
Okay.
tangent space completely and how do we use the corresponding forms. Yeah.
Okay, thank you.
Yep, sure. If there's no other questions, I will just proceed. Any questions further regarding
No,
this
yeah,
one?
we're good.
Okay. So so others are kind of important, but let me try to explain the Gaussian curvature first. Gaussian curvature first, and then let me just go back to 3 and 4. 3 and 4 are, you can just assume those are just the computational machineries. Not that important in my opinion. So you just need to get the sense of the Gaussian curvature. So
Oh,
now let me now explain step 3 for the Gaussian curvature. And this is today I need to just explain for your like the future study, right?
mm,
So
yeah.
this concept is very like the astonishing. So I want you to compare that. So
Wait, what's this? So I permission. It does not control.
may I just wait a bit or
Yeah, sorry, she has another phone
yeah, yeah, yeah,
she's
yeah,
like,
sure,
I
sure.
can't see.
Mhm.
Okay.
She should be almost done. So,
Yeah, yeah, yeah. Take our time.
mm,
Preserve the Texas.
yeah, I guess while we're like waiting, I'm just wondering like for do you mind looking at like an actual question on the problem set?
Absolutely. So let's just look at the problem set
Oh wait,
together.
she's done. Sorry, never mind. We can go back.
Good. All right. So I have to call you. So
That's
It's absolutely fine. It's very understandable.
okay.
get one more.
Wait, he's gonna go over the Gaussian curvature. Yeah.
So let me just repeat. So for the necessary experiments of the quantum computing, so all those are based on the values of the Gaussian curvature. And the Gaussian curvature is completely computed from the first fundamental form. So that's why I explained first fundamental form EFG. Then those like the steps of the crystal symbol and Riemann curvature tensor, of course, those are very, very important for sure. But for us, we will just use those as just a purely computational machinery. So today I need to explain what is the concept of Gaussian curvature and how do we use the those like the crystal symbol and the Riemann curvature tensor to proceed the computation. Is that okay with you? So this concept is very astonishing in the following way. So if you have a two-dimensional sphere. So, but yeah, before I proceed, let me ask you one mathematical question. What is the curvature? Of course, I didn't define this yet, but so curvature, so we usually just try to distinguish three different types of the curve. One is like straight line like this, and another one is like the such a function of the exponential function, and another function is like kind of the natural log, like the such a like the function. So we'd like to distinguish those three curves by looking at the concept of the curvature. Let's just go back to the calculus class. Then how do you distinguish those three curves? So if you have this point, so what's the difference among these three? How can you distinguish them?
Uh, like the vertex of wait, I'm not sure.
Yeah, yeah. So I'm just asking very naively. So from the calculus point of view, one variable calculus. So sure you did lots of such a like computation before. So how do you distinguish those like the three different like curves mathematically?
Is it like second derivative?
That's the answer. Yeah, very
Oh,
good. See, for example, the this like the case of the straight line, second derivative is just what? Just zero, because the slope is just constant. And the first case, the slope is now increasing, so that the second derivative must be what? Positive.
positive, yeah.
Also, last case, second derivative should be what?
Negative.
Negative, because the slope is now decreasing. So that the concept of the curvature, you can just assume this just is just nothing but second derivative value of a given function. That's the intuition. Is that okay with you? That's the concept of
Yes.
the curvature. Then now what? So now we are having either the sphere or the torus is a two-dimensional object. It's not the curve. So that still we'd like to talk about the curvature on the surface, not the curve. Then how can we proceed? This is a way to do it. So if you have the sphere, if you have a sphere like this, let me choose. So we are just looking at the sphere that's just here, not the inside. So on the sphere, let's just choose arbitrary point. Then you can just make the tangent like the space. And let me just explain this way. This might be much easier. So for each point, then just look at each curves passing through this point. How many such a curve? There should be infinitely many in general.
Infinite. Yeah.
Yeah,
Okay.
infinitely many. Then what can you do is that for each curve, we are able to compute the second derivative for sure. Does that make sense to you? Then how many
Yes.
second derivatives? Infinitely many.
Infinite.
As there are infinitely many curves passing through the target point. Is that okay with you? Then mathematics, especially spectral theorem in linear algebra, you can just cite this like a fact. Spectral theorem of linear algebra guarantees there is a maximum of curvature, of course, of some curve, and also a minimum. Why this is non-trivial? Well, there are infinitely many choices, so that it might be hard to find the maximum and the minimum. However, there's a general theory that guarantees that there's a curve that will give you the maximum curvature at that point, and also there's a curve that will give you the minimum curvature. Is that okay with you?
Wait, I have a sorry, are the curves like on the surface of the
Ah,
sphere or
that's an
is it
important like question. So, or we assume all curves are sit on the surface.
so wouldn't the curves like maximums like are all the curves like the same but in a different
That's
direction or am
very
I
like
like
the yeah, valid like the observation. So let me, for example, draw two different like situations. So for example, if you have a surface like just in R2 surface, if you just take the plane, basically just a plane, then we know we can draw like this plane, as you already know. Then if you take the point, for example, at the origin, then for example, you can take this straight line. Curvature is clearly just a zero, and you can take this straight line as well, right? Let me just compare with another surface given by the cylinder. So cylinder, I just mean not the inside, but just the outward. So that if you draw such a like the cylinder like this, and let's just choose the point, say over here, then there are two different like the types of the curve. One is straight line. You can take this straight line whose curvature is clearly zero. However, there's a this type of the curve, like the enclose this point. Does that make sense to you? This curvature
yes.
is not zero for sure. Is that okay
Yeah.
with you? So
Yeah.
it looks a little bit different, as in a sense that so for R2, it seems like there are a bunch of the straight lines, so that all curvature are just zero. Whereas on the cylinder, so there's at least a curve that makes the curvature not zero. So it seems it's distinguished, but let's just proceed further. So because of the like the sphere, so it is very like the symmetric, so that you can guess, oh, our curve seems look very like the similar. That's very like the valid like the observation for sure. But anyhow, general theory guarantees that the maximum and the minimum of the curvature there exists such a like the two, at least those two curves exist. So what is the concept of Gaussian curvature definition? Gaussian curvature is mathematically very simple. I mean, conceptually curvature of a surface at each point on that surface, Gaussian curvature at that point is the product of max and mean curvatures. That's the definition. So just to understand it conceptually, computation is that's why we are doing this problem set 2. Computation completely different like the issue, how to really proceed to get this like the quantity. But the definition of the Gaussian curvature is the following. So you just extract the maximum curvature and the minimum curvature among the infinitely many choices of the curvatures and just multiply those two quantities. That's it. And let me now just go back. Why
Can the
this?
max and min be the same
That's
or
possible. So it does not mean that there
okay.
exists unique curve, but
As
there
long
could
as
be many curves that gives the same like the maximum and also the same minimum values,
okay, like a sphere.
like the sphere. So now you can see the subtlety here. So if you look at the surface as just a plane, what is the Gaussian curvature? You can kind of make the reasonable guess that Gaussian curvature is zero everywhere because you can always extract the straight lines. Does that make sense to you?
Yeah.
Whereas if you look at now the cylinder, if you look at the cylinder, so even there is a curve look like this, but always you are able to find a straight line like this.
Yeah.
So if you multiply those two curvature values, what is it?
Zero.
Zero. So as a surface, so this is my plane, just a plane, just a blank like the paper. So you can just fold like this.
Oh,
So geometrically, they are the same. We are not distinguishing this like the
oh,
cylinder from the plane. And
ah,
how we can say it? Because Gaussian curvature are the same. So we
Okay.
introduce the quantity of the Gaussian curvature to say if Gaussian curvature are different, well, there are different surfaces. So that's why we are proceeding computation of Gaussian curvature of the sphere and the torus that you can conclude that they're really different. But in such like a scenario that as long as they share the same Gaussian curvature, it turns out that they actually are coming from the same surface.
Okay. I can't make that like plane into a sphere.
Exactly. That's not possible. So the
Okay.
Gaussian curvature of the sphere is always positive. So it cannot be zero. So that's the way we can distinguish from the sphere to the plane. So sphere
Okay.
is not the same as the geometry of the cylinder,
I
but the
see.
cylinder
That's
is same
pretty.
as the plane. This is nice like a machinery, right? So
Yeah.
So here's just the point that you just need to know. So I don't want to explain all philosophical detail of the Crispr symbol and the Riemann curvature tensor. What's the explanation for it? We really want to compute the value. Now you understand the concept. So in your presentation, so you need to introduce the concept. So I'm talking about you two both. So you should explain the concept Gaussian curvature as I explained, but the computation completely different like the recipe so that by following like this like the recipe, so the way to do it is we have EFG, so that we have the inner product on each tangent spaces. Then there's a way to compute the CRISPR symbol. Then there's a way to compute the Riemann curvature tensor that will give us the value of the Gaussian curvature. Like the behind story is very, very deep, but you just need to know how to compute. You understand what I'm talking about? So now
Okay.
let me
Yes.
explain just a computation recipe. So all I want you to do, because time is very like the short for you to really digest, just try to get the experience of the computing all those like the quantities of Gaussian curvature. Let's look at the problem set two.
Uh, yeah, wait, could I like ask the question about
Sure.
I was solving computing the Christoffel
Symbol.
symbol and I think wait, I understood everything except for like when I was asking like chat, some of
GPT.
them are just equal to zero.
Mhm.
Wait, how do I like tell without actually working through it that it's equal to zero? Um,
You
like or do I have
cannot know it
okay,
unless if you really do the computation. So
okay.
there's no way to avoid it. And because the
So
setting right now is so like the simple for the two-dimensional sphere and the torus, so most of the CRISPR symbol might be just a zero. There's just a few terms,
yeah,
not just a zero. But the intention that I want you to do is really just track by yourself. Just that's it. It's just
okay,
just
okay.
taking derivatives. So let's now look at the problem set two. So now I assume now this is a situation. If you don't get it, let me know. So you have two like the examples that you should proceed. For the sphere, you know R of UV. UV are now taken as two angles that represent each of the point on the two-dimensional sphere. Is that okay with you? This is a concrete description of the R of UV that I explained today for the
Yeah,
sphere. You know this. So I want you to convince yourself that if you have this description, can you compute by yourself for EFG? Let me just show you the expression of the EFG. Again, EFG just means R sub U dot R sub U, R sub U dot R sub V, R sub V dot R sub V. Can you do it? So this is the experience I want you to get. This is simple, but this is a very important, crucial computation that you need to do by yourself. Is it okay with you?
okay.
And
Yes.
also,
That's question one.
yep, that's the intention of the like this problem set. Also for the torus to compare from the sphere that you will do the experiment eventually. So this is the also concrete expression of the parameterization on the torus. So on each R sub UV, then you have this concrete like the explicit formula of each components. Then let me just repeat. Can you also compute EFG? R sub U dot R sub U, R sub U dot R sub V, R sub V dot R sub V. I'm not talking about the meaning. I'm just saying, just proceed the computation. That's it. Okay.
Yes.
So because we only care about the value, and then now you know this. But even though this can be easily seen, even you can just find this answer from just searching on ChatGPT. I want you to do it in your hand. This is important experience.
Mm-hmm.
And then next question. What is this? This is like a ugly one. So let me now explain how to. But this is mandatory. You need to gain this experience by yourself. So let me explain how to proceed. So please do not even try to memorize the expression of the Christmas symbol. That's not necessary. Just a copy, by looking at it, just a copy. So what you can see is that just accept this as just a fact that gamma ijk is written by this massive one, g sub superscript kl with, let me just copy. So it's indeed super massive for sure, as you can see, but still you should do it. That's the entire intention of this problem set. By the way, for the other team, I will not ask them to do this because their projects are different. But eventually they will work on the same like the two-dimensional sphere in a different context. But your project depends on the value of the Gaussian curvature. In order to do it, you need to compute this one. But for the others, they do not need to compute this one. So projects from set are different from here. So you should just think of this G as a first fundamental form. So the first fundamental form consists of the EFFG. Is that okay with you? EFFG, and E means R sub U dot R sub U. F means R sub U dot R sub V, and G means R sub V dot R sub V. I assume you compute all this by yourself. So just replace this in this way. So this is same as G sub 1, 1, G sub 1, 2, G sub 2, 1, G sub 2, 2. Especially you can see G sub 1, 2 is always equal to G
The
sub 2.
G sub. Oh, okay. Ah, okay. I see.
Now you know this. And then what is the meaning of this superscript? This superscript means the following. So take the inverse. Then you know the inverse matrix. Inverse matrix always determinant exists in this case. So that please do not like get confused that always EG minus F square is always positive. So do not worry that this becomes zero. That's not happen. And then this just means GE negative F negative F. I'm just talking about the inverse matrix. You know what I mean?
Yeah.
Then this is just written as G sub superscript 1, 1, G sub superscript 1, 2, G sub superscript 2, 1, G sub superscript 2, 2. Then you can just assume ijk and also L runs either 1 and 2 because we are now working on two-dimensional surface. So for example, let me just show you just a few cases. So for example, if you look at gamma sub 1, 1, 1, just plug in everything. So how many choices that you need to compute? 2 times 2 times 2, 8 choices that you need to proceed our computations. So say gamma sub 2, 1, 1, gamma sub 1, 2, 1, gamma sub 1, 2, 2, gamma sub 2, 1, 1, gamma sub 2, 1, 2, gamma sub 2, 2, 1, gamma sub 2, 2, 2. You need to proceed, write all this out.
So L is like not in like the
Not in
gamma
the indices of
notation.
IJK. That's a different, like the independent, like the index that I will explain.
Okay.
And in the left-hand side, as you pointed out, so there's no L, so that you need to understand what is it. So then now let me just copy the expression. Then this means 1/2 of G superscript 1L, and you will get partial derivative. So ij are all equal to 1, so I will get 1L dx1 plus round dg sub 1L divided by dx1 as well, ij are equal to 1 in this case, minus round dg sub 1, 1 divided by this guy. I just copy with just replacing our indices. Is that okay with you up to here? Then you just need to
Yes.
understand what is the meaning of the L here. So this is the convention in differential geometry. So there are two L, basically. Two indices means summation. That means the following. So let me just copy. So let me just put this over here. So this means, so let me just copy here again, because I'm just lazy.
Where L is 1 and then L is 2.
Yep, that's it.
Okay.
So that you just need to just make, let me just now erase all of them for regarding L. So here's a L, here's a L. There's a L. Let me just copy this expression here.
So we need to do this like computation like almost 8 times or like
Exactly.
4 times because
So,
wait, some of them are the same, right? Like
yep.
gamma 212 and gamma 221 or something. But
So,
uh
let me explain my intention so that you can twist in your own way the reason that I want you to do this computation in your hand, even though there are lots of the overlap. Is that so? Eventually, the experiments you will do is definitely you will just need to proceed with the like the computation or like the recipe from the code. You will not do this in your hand eventually, but now you can get the sense of what was really going on behind for this like the simplest possible case. So if you just rely on this computation by just using computer, then you do not really have a sense of what was really going on in this level. So that's why I highly recommend you to do the computation in your hand, even though there are lots of the overlap and you can find the symmetry, then some of the quantities are just the same, some of them are just zero, but still later on, this computation could be very ugly. So that I will not let you do in your hand. You need to use the computer coding for sure, but for a moment, you know what I mean? So at least the case of the two-dimensional sphere and the torus, in this like the simplest possible framework, you can do this in your hand. And now you see
okay.
how to proceed for the others, right?
Yes, I understand.
Okay. So now let me just go back to the problem set. So in this way, so for each CRISPR symbols, there are two parts of the summations for each. For eight functions, so
Okay.
that you need to do all computation in your hand. For the two-dimensional sphere and torus, you might not like it, but when you just feel exhausted with the like the conversation with the friends, just sit on your desk and just it's
What?
tedious, but just do it. Okay, so that's the way to learn. And
Okay.
let's now go back to the problem set. So now you understand how to proceed this computation.
Yeah. Wait, so the like knowing what like the indices actually mean, like we don't need to know.
I'm very happy to explain, but not before July. So if you too want to
Okay.
proceed this project, I'm very happy to explain later on. But because of the time limitation, I don't
Yeah.
want to explain.
Okay, that's it.
Yeah,
Thank you. Yeah.
that's the only reason because time is so limited. So
Yeah.
now let's now try to see. Now I assume without understanding any meaning of it. And for the again for the presentation in front of the others, you can explain the conceptual explanation of the Gaussian curvature, and you can simply just say, well, the computation rest is completely different, like the story, and this is just the way of the really computing everything. That's what you need to explain, but not like the what's the philosophical like the meaning of the curvature symbol and whatsoever. But later on, you'll see. So now I assume you know each like the CRISPR symbol, like the terms. Is it okay with you? You know this?
Yeah.
And then now you can get this. Do you agree?
Okay.
I know
Okay.
this is kind of a
Um,
forcing.
oh,
I know it, but this is exactly my intention to proceed. So it takes more than semester to really digest if you want to approach with the meaning of it. But yeah, this is the Riemann curvature tensor component that is completely different from this right hand side. So each like the terms are the functions. So then you can take the partial derivative with respect to two indices, then just put it together. And now the only difference is that so there is a I, J, K, L. They are fixed indices. So how many like the functions you need to compute? There are 2 times 2 times 2 times 2, 16 functions that you need to compute. Okay, for each surface and torus. And if you look at this expression, there are two indices regarding M, meaning that there are two summations. So proceed the computation. Then you'll get this. Are you with me?
Mhm.
So just tedious, but again, this could be very, very helpful. So please do not like the think so this is so like the obvious or just tedious, even though it is so too tedious, just do it. So the only last thing, so now you reach out to the concept of the Gaussian curvature, but there's a one single last step that you need to know. So if you look at the position of the indices, there's a superscript, and this unpointed, there's no superscript. There are all those like the
yeah.
in the bar.
Confused.
So there's a one more step that I should explain. So But once you get this, like this guy, then this will give you the Gaussian curvature completely. So this is a computational recipe. Now let me explain.
Oh, it just gives you the value. Okay.
Yep.
Okay.
So,
Cool.
let me just skip this part. And now you know R sub ijkl can do it. We can do it. It's
Okay.
lengthy computation.
Okay.
Nice.
You can do some sarcasm for sure, but yeah, you can do it. And then this like the determinant of G just means so determinant of E F F G. So this part is already over. So because you already know E F F G, so that this just means E F E G minus F squared. You get this. So this part is done. The denominator, there's nothing to worry about. So what is R sub 1212? So I'm not sure I put this somewhere here. I didn't put this here. So let me just show you one just a reference that if you wanna look at in general. So let me just search as a formulas of Riemannian geometry. So let me just first like the copy on this like the chat like the link here first, and let me just show you. It doesn't mean that you need to study it. I didn't mean that at all. This is just for your own reference. So if you just look at this guy, so just skip everything. So he invented everything here, and
Yeah, okay.
uh, I assume it should be somewhere here. Sorry, not this guy. I'm talking about yeah, list of yeah, this is what I'm looking for. Now you can kind of the see what you kind of now understand what are each like the formulas, especially what we need. Let me try to find it. So this is the form. Now you know what this is. For R sub ijk with the superscript L, this is the same expression if you just compare. And then
Yeah.
I just need to show you the R like the subscript should be somewhere here. Of course I know it, but I just wanted to show the expression. Yeah, this one. This is the expression. So now let me just write it. So then now you have a reference to look at if you are curious. So this is written like this. So if I just copy with the indices of 1, 2, 1, 2, because this is all we need for the computation of Gaussian curvature, then this will give you equals R sub 1, 2, 1, 2, 1, P, G sub P, 2. That's the meaning. I just copy from the formula that I show you. Then there are now two indices regarding P. What does that mean? Summation. So that this will give you R sub 1, 2, 1, 1, G sub 1, 2, plus R sub 1, 2, 1, 2, G sub 2, 2. That's the meaning. Am I right? Yeah, I'm absolutely right. So this equals F, this equals G, by the way. And you already know this guy, so you know each of them. You know what I'm talking about? So let's just look at the big structure. So now you see, you know the first fundamental form, EFG, capital E, capital F, capital G, you know it. Then you also know G inverse, inverse matrix. It's just nothing but the inverse matrix. Then you know the Kurzweil symbol. Then you know, so well, for your own record, let me just give you the expression. So this guy is written as, so I never try to memorize this expression, even though I know the just general pattern. So just look at it and just copy. Look at this. So you know this, then you know this, then you can
Yeah.
compute the Gaussian curvature. So this is a logic. So
Okay.
you will see, so for a moment you might feel very uncomfortable with why I need to do this. So again, the reason is the following. In the context of the computing, the classical computing uses the so-called classical bit. So it should be either zero or like the one. And in the quantum computer, it replaced the classical bit of the concept of the zero, one to so-called the concept of the qubit. In the concept of qubit, if you consider the collection of the one qubit later on, so this becomes the two-dimensional sphere. You can see this after doing homework problems at 3. So it takes time to do it. And what I'd like to let you do is I know how to change the setting in a general way that instead of the standard setting, I will give you the generalization, how to generalize the known setting. Then, or like the quantum computing experiment becomes like the different, it's just a different. So that can be done for the undergraduate. So the like the purpose is to just compare this generalized like the two-dimensional sphere for the one qubit like the set in the like the context of the looking at the Gaussian curvature value. Then, so let me just explain why you should, yeah, why this is very worthwhile to try for the undergraduate. Two reasons. Of course, you can now at least you convince. I hope you convince yourself that you can do the computational Gaussian curvature for sure this week. Not after a year. You can do it this week. This week. This like the week that can be done.
Yeah.
Yeah, even you feel it's a kind of the torture, but still it can be done. So the reason is that so for the standard like the theory and the standard setting. So if you compute the Gaussian curvature of the two-dimensional sphere is just constant positive, just a positive like the equal to 1 or positive 4. That's not really beneficial for the quantum computing. So what I will let you do is I know how to just change the sphere setting a little bit so that it just changes the Gaussian curvature everywhere. That affects the performance of the one qubit circuit. So it's the comparison between the standard one. So what you should do this week is that so you just need to confirm that for the just a standard like a two-dimensional sphere, Gaussian curvature is positive everywhere. It's just constant. That's not really handy for the quantum computing. So what you will present, I mean, on the end of the July, and I just want you to do proceed, just between you two, not adding any like additional participants, is that so now, so we want to replace the bit by the qubit, and when we just consider the geometric structure of the one qubit, it becomes a two-dimensional sphere, and in that case, the Gaussian curvature is just positive constant. And that's not really handy for the performance of the some of the performance of the algorithms of the quantum computing. So what we propose is that we will just change the two-dimensional sphere just a little bit in a natural way of the context of the quantum computing. Then if we proceed well-known experiments, especially two experiments, then you can compare and that comparison already gives a new result. And that's I think this result. And yeah, that's what my intention is for. So now you can see why I just wanted to proceed this computation. Eventually, so or like the Gaussian curvature quantity will be changed depending on the point. But this week, I wanted to do everything in your hand to just confirm curvature just becomes constant for the sphere. Torus is not constant. And later on, it's not constant even for the sphere for our like the real experiments.
Okay. Okay.
Yeah. Any questions or comments?
No. Wait, what? On the problem set, what are like the questions that are asking about like area? Like, like what are they meant for? Like, I don't know, why are they important? Like calculating the area and the surface area and stuff.
So I want to just give you two answers for that. So the most important part is just the computation of the Gaussian curvature.
Okay.
And it's about the geometric structure of the given like the underlying like the spaces, either the two-dimensional sphere or the torus. So another like the question I need to provide is eventually all those are related eventually. So for a moment, all we just want to do is I just want you to just confirm the computation in your hand. And later on we will see how these like quantities come up with a certain like the part of the algorithm later on, but I don't want to like to justify each like the step, but it just takes time. So just check the computation, and as you know, solution might be completely wrong. So that just please suspicious of the computation and just check, do just a calculus, just that's it.
Okay. Okay. Thank you.
Okay. Yeah.
Sure. the record.
Yeah.